Hello everyone, welcome to my channel. I'm John. Today we are going to talk about the Boolean algebra and the basic logic gates. We know that in math, the algebra is defined as the study of mathematical symbols and the rules for manipulating these symbols. For example, the solution of the degree 2 equation in order to solve for the value of x, we have this expression, right? We need to follow this rule to get the value. So if we have a similar system of algebra to deal with Boolean variables, then we have Boolean algebra. In some textbook, it's called switching algebra also. And the Boolean variables is a special variable that has only two logic states, either low or high or 0, 1, on, off, true, false. Yeah, you can express it in different ways, but it only has two values. That's important. And for the n variable system, there are 2 to the power of n possible ways of assigning the value to the n variables. Give you an example. Say if we have a one variable system, the variable name is a, because it's Boolean variable, right? So the only value it can get is either 0 or 1 or high or low, whatever you call it. Okay, so that's a 2 to the power of 1, two possible values. If I have a two variable system, say one variable a and another variable b, then I have different combinations. So a could be 0, b could be 0 2, or a be 0, b to be 1, or a equal to 1, b equal to 0, or a equal to 1 and b equal to 1, right? So four possible ways. That's 2 to the power of 2 variable. If I have three variables, say a, b, c, then I have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. So totally 1, 2, 3, 4, 5, 6, 7. What I miss? Okay, I miss 1, 0, 0. Right. So totally 8 combinations. That's 2 to the power of 3. If you have n variable, then that's 2 to the power of n possible ways of assigning the values to all variables. Okay, logic operators. Just like regular algebra, we need operators, right? Like the plus, minus, or multiple or division symbol. So in logic operator, we have similar thing, but they are treated in a different way. So like the first one we talk about is that we have the AND operator, and this unit has the same symbol as the multiplication operator. Like sometimes we use star, sometimes we just use a dot, or sometimes we don't even put anything between the variables, right? And we have OR operator, which is same as the plus sign, but be careful, we don't read it as plus, we read it as OR. And we have NOT. So NOT means the opposite of its original value. Okay, and to represent NOT, in most of the textbook we will see that we put a bar over the variable, but also in quite a few books we can see it written like this. Okay, and also you might see things like that, but to remember they are representing the same thing, just the opposite value of the variable. Okay, and besides the operator, we also need expressions. The expression basically is made up of the variable and the operator. So for the add expression, we have, say, a and b, or we can write a and b, or like I said, we don't even need to write the operator every time for add. For all, we all write A or B. Not, we already talked about, we can write A bar or A prime. And also, in order to represent the Boolean expression in general, so we kind of introduce the function, like the dependent variable, you can think. We know that in math, in most cases, we have the dependent variable represented as like using y, right? Maybe some other letter like z, or in more general format like fx, right? So we can do the same for Boolean algebra. And if we have multiple Boolean variables, if a multiple variable system, we can also write something like say a1 or just a, b, c, whatever. No matter how many variables you have, you can put it there. So those are stand for the input variables, and f means the output function. Okay. The last thing in this slide I want to talk is about the orders, like the precedence of the operations. So generally we follow this. If there are no parentheses, we always handle the not operation first, then and, finally or. For example, if we have this Boolean expression, okay, so the first, say we have a function. Okay, in order to figure out the value of y, we need to solve a prime. Okay, and the second, then we take the value we get for a prime and to add it with b. Finally, we have the result of a prime b or c. However, if we have the parentheses involved, then we always handle the parentheses first. Then we do the not. Finally, we do the and here. Okay, very similar to math, right? Okay, now let's talk about one of the most important tools in digital logic design. That's the truth table. It's very important because first, it determines it tells all the details about how your system works. And second, how to interpret the truth table kind of determines how efficient your hardware is, because your hardware design kind of based on the translation of the truth table. Okay. So what is truth table? It's a list of all possible input values as well as corresponding output. So like I just said, it tells every details of your system or logic circuit. Okay, I give 3 examples here showing the truth table of the 3 basic Boolean function, and, or, and not. So here a and b are the input variables, and the y is the output variable. So basically you can think there is a circuit. We have 2 input, we have output, 1 output. So this is about how we determine the output value based on the input values. Okay, so we list all the possibilities because for 2 variable system we know that we have 4 possibilities, right? And for the add function, basically the y value is equal to 1 only when the input variable a and b are both 1. Okay, so you probably need to remember this. This is a simplest truth table you can get. Okay, similarly for all function, we still only involve 2 inputs here and 4 combination. In this case, the output value will be 0 only when both a and b are 0. Okay, so this is a quicker way to help you remember the truth table. Okay, and for not, basically you can only have 1 input for not operation or for not function. So you only have two possible input values, then two possible output values. Okay. Now the question comes that if we have a Boolean function more complicated than just AND or not, like a combination of them, how do we find out the truth table quickly? So basically here we will use what I just talked about. Use the simple way to remember, help you remember the two input and or gate and or operation and not function. Yeah. So let's use an example to explain this. But before that, you should also know that for the given Boolean function, we have different ways to represent it using an expression. So we have different expression to represent the same Boolean function. But no matter how we manipulate the expression or change the expression, the truth table is always unique. Okay, so like I said, again, the truth table is the most important thing. Tells everything about your system. Okay. One example. So basically, later we will see this expression is actually equivalent to this expression, but they are two different expressions. However, they share the same truth table. That's why they are equivalent. Okay. But how do we find out the truth table for a complicated function like that? So let's look at the example here. Say we have a three variable system, f, a, b, c equal to a and b, or a prime and c. So if you remember the precedent, the order, how to solve the Boolean algebra, okay, we know that we handle the not first. Okay, so let's do the not first. So a prime means not a. So basically that's easy, right? So it's just the opposite of the a value. For every a value, we just need to take the opposite value. Then let's handle the add function. We have two add functions here. The first a and b. So then we got two input variable here, right? So we can use this truth table. Let's use this truth table here, and I showed you how to quickly remember this. So the y value will be 1 only when a and b are both be 1, right? Then that's easy. So we're just looking for the combination for a and b where they are both 1. So we got these two guys here. Then we can put 1 on these two. For all other cases, the output for a and b will be 0, right? Similarly, let's try with the a prime c. So a prime, the value for a prime is listed here. So again, this is the AND function. So if we want this output to equal to 1, which means the a prime has to be 1 and the c has to be 1 at the same time, right? Then we're just checking this column and this column to see when both they have 1. So like here, then we put 1 here, 1 here, we put 1 here. Do we have others? No. So all other values should be 0. Okay. Finally, we got a and b and a prime c. Then let's put them together using OR function. Then we need to check this truth table here. Again, the quick way to remember this, the y value is 0 when both a and b are 0 at the same time, right? So here a and b actually is this part and this part. So we need to look at, maybe I change the color. So this time we need to look at these two columns to see when both these columns show 0. So we got here, and we need to put 0 here. 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, I believe that's it. So all the other blank arrow, we need to put 1. So finally, we found out the truth table for this function, which is this column. I'll use a different color to draw that. Okay, now let's look at the logic gates. So logic gates basically is a physical realization of our Boolean functions, like the and, or, not. This is a physical realization, so like the real circuit to realize that function. Okay. Basically, what you see here are the symbols to represent those circuits. The real circuit doesn't look like that. The real circuit involves the knowledge about transistors and resistor, the basic circuit component, and that's beyond the scope of this course. So here, we just use those symbols to represent that circuit. Okay, so those are called gate. And there are two different symbol systems. Like one is called distinctive shape, so you can see the shape of a different function is different, right? And the other way is called a rectangular outline. So the shape is all the same, but we put some extra stuff inside the rectangle to separate different gates. So in most arrow, I think the distinctive shaped representation is used, but still in some country or location, they still prefer the rectangular outline representation. But in our course, I will use a common one here, so the distinctive shape. Okay. So basically, those 3 gates represent the 3 basic Boolean operations. Okay, and here just shows an alternative way. If you don't know the detail about the circuit inside, but you can think the basic gate in this way. So for AND, you can think you have a simple circuit to control a lamp, but you got 2 switches here put in series. So in order to turn on this lamp, turn on means 1. In order to turn on this lamp, you need to short the switch A and B at the same time. When you short it, you can put both A and B in the on state or the 1 state. So 1 1, you get 1 here. For all, you have like parallel switches. In order to turn on lamp, in order to get a 1, you just need short 1 of the switches. So that might help some of you to understand the operation. If we put multiple logic gates together and make proper collection of them, then we can realize specific Boolean function. And the graph we get is called logic diagram. As shown on the right, we can see some example. This is a simpler diagram, and this is a more sophisticated diagram. Okay, and also we have different levels in the logic diagram. So basically, more levels we have, the slower the circuit we got. Okay, or we say the delay of our circuit is bigger if the levels are more. Okay, and the delay is a very critical design parameters in digital circuit. So if you are a design engineer, when you are designing some digital system, delay, you must consider how to minimize the delay among the gates. Okay, timing diagram. So before the previous slides, we talked about the logic diagram that shows the collection of the using logic gates, right, to realize specific function. But the timing diagram basically represents the input-output relation, but as a function of time. So before we have a truth table listed out everything. We should know about that system, how it works, how the output change with the input, right? But here we just use a different way to represent that. So as a function of time. So let's see what I'm talking about. Okay, say we have a simple logic diagram like this to realize this function here. Say we have the input signals. So we have how many inputs here? We have a variable A, variable B. B prime basically is the opposite of B. And we have C. So basically we only have three input variable here, and this is the output F, A, B, C equal to that. So say we have input A, B, C, and these signals could change with time. So if we have the x-axis as time, so the value of A may change with time. It may start with a high, then at a certain point become low, then at a certain point it become high again, right? So we use these lines to represent the logic level. So if the line is above, we know it's 1. If it's down at the bottom, we know it's 0. And let's say we have specific the value changes at a specific moment. Say T0, T1, T2, T3. This actually what happening in the real circuit. The signal value will change. For B, it changed different ways. So like it first start with 0, 0. Then at T1 it becomes to 1, and T2 keep 1. At T3 it becomes 0 again. Okay. C, we also give an example here. So let's say C changes like that. So we got 0, 1, 1, 0, 1. So the question is, how would the output change? Okay. We can use similar way as we figure out the truth table to handle this. So let's solve this diagram by levels. Okay, start from the easiest one. So the lot function. So B naught should be the opposite of B, right? This is also true when the time changes. It's always true here. So B prime should be the opposite. Then it should look like, maybe use different color. So it look like that. So totally opposite at B. Okay. The A and the B prime. How do we find out the diagram for this? So if you know that this is add function, but the two variables is A and B prime, right? If you think about the property for add function, the output for the add function will be 1 when both input is 1. So then we just need to look at to find where both A and P prime to be 1. So like here, so we should get 1 here. 0, 1, we should get 0, 0, 0, 0, 1, 0, 0, 1, 1, so we get 1. So now we know how to draw this. So we start with 1, then at T0, change to 0, then keep 0, then at T3, change back to 1 again. Now let's try the last one, A, B prime, or C. How about this one? So this one is the OR function between this and that, right? Now let's recall the property for OR function. the output of all function will be 0 when both variable are 0, right? So we got, then we get, let's start from here. So we got 0 here, but we got 1 here, which means the output will be 1. We got 1, 0, still be 1. 1, 0, still be 1. 0, 0 should be 0. 1, 1 should be 1. So finally, the output should change this way as a function of time. So that's what the timing diagram means and how you solve it. So besides these 3 basic logic gates, we also have other commonly used gates. If we add a NOT gate to the output of the AND gate, we get a NAND gate. So NAND basically means not AND. And so you will know that its truth table basically is the opposite of AND. So C is the output of the AND gate here. So if you remember, we have 0, 0, 0, 1, right? Then Y should be 1, 1, 1, 0. If we add a NOT gate to the output of OR gate, we got a NOR gate. Basically it means not OR, so the opposite of OR. So again, if you remember the truth table for OR, that's 0, 1, 1, 1. So this time we got 1, 0, 0, 0. Okay, so why do we need these two? In reality, actually, in most cases, we prefer to use NAND and NOR gate, not AND and OR gate. The reason is that it's actually easier to fabricate NAND and NOR gate in the integrated circuit market. Okay, it's easier to fabricate. Actually, it's more it needs more work or more cost to fabricate AND and OR. So that's why actually people prefer using NAND and NOR most of the time. And also we have a special logic gate called XOR. So XOR is not really one gate circuit. It's basically composed of multiple gates, okay, to realize a specific function. And if you check this logic diagram here, you will get the output function equal to this. And this we have a special operator to represent the XOR. So we put it as A, we'll read that A XOR B. But in nature, it can also be written using AND, OR, and NOT function. Okay. So let's try to figure out the truth table for this gate. Again, let's start from the AND function here, A prime and B. Okay. So how to write the truth table for this quickly? We know A prime is basically the opposite of A. So in order for this AND function to be true or to be 1, which means A prime need equal to 1 and B need to be 1 at the same time, which means A has to be 0, B has to be 1. Then we just try to find where A equal to 0, B equal to 1. So here we put a 1 here. Then that's it. All the other has to be 0. Similarly, for this add function to be true, A has to be true, B prime has to be true. So we are actually need to look in for the combination where A equal to 1, B equal to 0. Because when B equal to 0, B prime is 1, right? So this should be 1, then the other should be 0. Then we put these two using OR function, then the truth table is 0, 1, 1, 0. So how to properly interpret this result? Basically, if you check the input and output, you will find that the output of XOR is 0 when the input are the same. So if we got 0, 0, output is 0. If we got 1, 1, output is also 0. Or put it in another way, the output will be true or 1 when the input are different. So that's how you remember it quickly. Okay, and just like the NAND and OR, we have XOR and XNOR. XNOR basically means not XOR. Okay, and also we have a special operator for that, like this. And we know that this equal to A XOR B, but we put a bar there. Basically means not, or you can write as A XOR B in parentheses, then put a prime. And if you want to represent this using just an AND, OR, and NOT, it will equal to something like this: A and B, or A prime and B prime. Okay. Why it's equal to that? We will talk about this later in later lectures. And also, I think I forget one thing is to show you the symbol for those 3 new gates. So for NAND gates, we have a special symbol for it. So it looks similar to AND, but we simplify the NOT gate as just a circle here. So this is the symbol for NAND. Similarly, we have the new symbol for NOR. Okay, like that. For XOR, we draw it like this. So just the OR gate, but we add an arc before it. So this is XOR. For XNOR, you probably already know, we just add a circle in front. Okay. Okay, so far all the logic gates we have talked about have 2 inputs only, right? Except for NOT. NOT always has 1 input. Okay, but for the others we have only 2 inputs. But what happens if we need more inputs? So basically we can expand them. For example, I can use 2 AND gate, say A, B, so the output is A and B, right? I can use 2 AND gate to cascade them to make a 3 input AND gate. So A and B and C is equal to, right? So using our analysis to find out the truth table, we will get the truth table look like this. See if this is equal to the function z, then we have and the change ABC to WXY. Okay, we have this truth table here, and we can do similar thing to other gates. But how do we know their truth table? So to help you remember their truth table, I can make this table here, talking about the truth table using simple sentences to describe the truth table for n input gates. For AND, OR, NAND, NOR, they are pretty easy to remember. For example, like for n input NAND gate, because it's the opposite of AND, so we know that the output is 0 only when all inputs are 1. Okay, or you can describe it in another way. The output will be 1 if there is 1 or more than 1 inputs are 0. Make sense? For NOR gate, the output is 1 only when all the inputs are 0. Or you can say the output is 0 if 1 or more than 1 inputs are 1. Some special one is the n input XOR and n input XNOR. For n input XOR, the output is 0 when even number of inputs is 1. So you need to count how many ones you have in the input variables. If it's even number, your output is 0. If it's odd, your output is 1. And XNOR will be the opposite. Yeah, so if you can remember this table, I believe you will know the truth table for all those basic gates. Here is an example to show you how we can quickly, using the sentence I showed you, to fill out the truth table. For example, we have I think I made a mistake here. Actually, we don't have E here. We are having 4 variables, A, B, C, D, right? So what function is this? So we have A and B and C and D, but with a prime. So this is a 4 input NAND gate, NAND function, right? So so if we go back to see the sentence, so I just memorized it. So for the n input NAND gate, the statement is that the output will be 0 only when all inputs are 1. So you just find the last case, all inputs are 1, put a 0 here, then all the others has to be 1. Sorry, 1. Okay. So you can quickly fill out the truth table. A second example, write the truth table for this function. Again, I forgot to delete this. In this case, we have 3 input variables, and this is the 3 input XOR function, right? So if we recall the sentence, for 3 input XOR, we need to check the number of ones in the input combination. If it's even number, we put a 0. If it's odd, we put a 1. So let's count. There's no ones here. 0 ones, which we just take it as even. So we put a 0 here. We got a 1 here. So we put a 1. That's odd number. This is also odd. So we put a 1 here. We got 2 1 here. That's even. So put a 0. 1. This is odd. Even, odd. So the truth table should look like this. Okay, that's for today's lecture. I know there are a lot of terms involved in this lecture, but knowing those basics is kind of very important for the upcoming lectures. So thank you for watching, and if you think my video is helpful, please like, share, and subscribe. Thank you. See you next time.